To truly understand the essentials of known physics, we are going to prove them through induction, through observation. But what we will find is that observations on their own are not enough. Newton didn't prove gravitation by watching the sun move through the sky and watching objects fall, and that's it. He had to reason from prior ideas. He had to look at such observations while reasoning with Copernicus's understanding that the sun causes planetary motion. He had to reason with Kepler's understanding of the patterns of planetary motion. So to perform induction, to reason scientifically from observation, you must make observations while reasoning with a huge wealth of prior knowledge. The key to understanding physics through its proof is therefore to show the observations and reasoning steps in a possible order of discovery, each idea being used as the foundation for each later idea. Before we do a rigorous proof of the essential ideas in physics, though, I'm going to give you an overview. I'm going to present to you the history of physics' discoveries in its broad strokes, forming the scaffolding for our coming skyscraper of knowledge. And what this will do is it's going to give you a sense of the content of physics, of the journey yet to come, and of the basic process through which it was proven, through a series of observations and reasoning steps, each built upon the last. So I hope that you'll join me on this beginning of my journey as we explore the history of physics. The first hero of this story, of the story of physics and astronomy, is a nameless one. Before man knew anything about science, before he was able to know the world and master it, the seasons were a mystery. Sometimes it would get hot, sometimes it would get cold. When it got cold, you'd run out of food, you couldn't plant crops, a lot of people would die. So there was a motivation to understand the seasons. When will winter come? When will summer come? When should we plant crops? When should we store up our food in preparation for hard times? So whoever this man was asked the question. Whoever this nameless genius was, and I'm guessing a lot of different cultures have a different genius who figured this out. But whoever he was, he probably noticed over the course of years that during the winter months, the sun was out less, for less time. And during the summer months, the sun was out for more time. And what he may have done is he may have tracked the temperature, writing down the temperature each day, and timing how long the sun stayed in the sky. Maybe he used an hourglass to do this. And what he would find is that the hottest day over the course of many years, the hottest day is always lagging about 2 months behind the longest day, the day for which the sun stays in the sky the longest. And so this may have confused him. He may have thought, oh, well, I thought the longest day would be the hottest and the shortest day would be the coldest day in general. Maybe it wouldn't be perfect, but you'd think it would line up. And then he realizes, oh, wait, if you put your hands near a fire, your hands don't immediately get hot. Your hands don't immediately get cold when you remove them from the fire. So maybe what's going on is that the longest day does, in fact, cause a hotter day. But it takes a while for the Earth to sort of heat up and reach its highest temperature. And so the first man, whoever he was, to be an astronomer, his contribution, whoever he was to find that the sun and the amount of time it shines on the Earth is the cause of the seasons. This would have led to more understanding, a tracking of the sun. Maybe what people did, and this is again in prehistory, people would have watched the sun as it moved through the sky. And maybe what they would have done is they would have tracked the speed at which the sun moves while it's under the Earth. And they don't know what it's doing under the Earth, but they say, well, if it keeps moving the way it was during sunset, what would happen? And then they time it out and they're able to see, well, the sun rises exactly in the location you'd think and at exactly the time you'd think if you keep track of this motion. Later, people may have asked, hey, the moon always looks different depending on what night. What causes this change in shape? And what they would realize is over the course of observations, they would be able to see that it's the position of the sun which dictates the phase of the moon. Whatever part of the moon is being lit up by the sun, that's the part of the moon that we actually see. And so we see that if the sun is close to the moon in the sky, we don't see the sun, or we don't see the moon at all, because it is the back half of the moon which is lit up. Whereas if the sun is directly beneath us, perhaps at night, and the moon is directly above us, we will see a completely full moon, since the part of the moon getting illuminated is completely facing us at that time. As you can see, there's these small incremental steps. And so as people are watching the moon, as they're watching the stars, as they become curious about the world, that this other world that we see in the heavens, they might notice one day that the moon gets shaded. The moon suddenly, during a full moon, the moon will become shaded. It will suddenly go dark and then red. So what the hell is the cause of this? And the Greeks, the Greeks then noticed that they were able to reason out that the reason this happens, this eclipse, this darkening of the moon, this unexpected darkening of the moon that doesn't go along with the normal phases of the moon, it happens always when the sun is directly below the earth. Remember, they didn't know the earth is a sphere yet. They knew the earth is just this thing that we're on. It was completely reasonable for them to say the earth was flat at this part of history. And so they would say, okay, well, during a full moon, the sun is always beneath the earth and the moon is above it. And when this eclipse happens, what they found, by tracing the actual positions of the various bodies, they found that whenever an eclipse happens, it's because the earth lies between the sun and moon. And so they see that the cause of the lunar eclipse is the earth blocking the moon from the sun's light. Now, over the years, this knowledge is known, it's passed down, until it reaches Aristotle. And what Aristotle, and so this is our first hero who's an actual historical figure, someone we actually know the name of. And what Aristotle did, what he might have done to reason this out, is he would say, well, hey, if the earth is casting a shadow on the moon, we should be able to know the size, we should be able to know the shape of the earth just by looking at the shadow. And what's found is that the shape of this shadow is a circle. So that suggests that we have a flat disk earth. But Aristotle thinks about this more and he realizes, wait a second. The eclipse doesn't just happen when the moon is directly overhead. The eclipse sometimes also happens, at an angle. Perhaps sometimes the eclipse even happens when the moon is quite near the horizon. Well, if an eclipse happened when the moon was near the horizon, wouldn't that make an eclipse shadow that was sort of a weird oblong shape? And it doesn't. Aristotle went through the various records. He found that no matter where the eclipse occurs, the shadow is always a circle. Now, what's the only shape that projects a circular shadow in every direction? A sphere. Aristotle confirmed that the earth is a sphere and all lands and seas rest upon its surface. This then led the Greek mathematician Eratosthenes to ponder the actual size of this enormous sphere that we live on. And by measuring the shadows of sticks in two different cities, and by measuring the distance between those two cities, Alexandria and Syene, by calculating the difference between those two shadow lengths, he was able to use geometry to calculate the size of the entire Earth's sphere. So already we've progressed an enormous amount as a civilization, as a species. Our knowledge has gone from not even being able to survive through the winter all the way to knowing the shape and size of the entire Earth. But the Greeks didn't stop there. Our next hero is Eudoxus, who created a model of the heavens, a mathematical system that was able to predict much of the behavior of what we see in the night sky. Eudoxus's system imagined a celestial sphere of stars which rotated around the Earth. And attached to that sphere was the sun, accounting for its motions as time progressed. But unfortunately, there were some problems with this model. There were certain stars which were called the wanderers, the planets. And these were stars which moved with respect to the other stars over the course of many days. And Eudoxus's way of understanding their motion was also to attach it to the sphere and have it move around the Earth in a perfect circle. The problem with this, though, is that the planets do not move perfectly around in circles when we watch them in the night sky over the course of many months. They do this funny loop-de-loop thing. They do this retrograde motion, backward motion. And so Eudoxus's way, unfortunately, of modeling this retrograde motion was to put each planet, each wandering star, on a little circle within its circle, on its celestial sphere. These little circles are called epicycles. And they were, unfortunately, sort of a mathematical way to preserve this idea of perfect spheres, which the Greeks thought and always attributed to the heavens, these perfect spheres, while also accounting for the observations. Unfortunately, this model persisted for over 1,000 years and in its own way stalled astronomy. But there was an astronomer who was able to move forward despite this. His name was Aristarchus. And what Aristarchus did is he knew Eratosthenes' number for the size of the Earth. And of course, he also knew that the eclipse shadow that was projected upon the moon is caused by the Earth. And Aristarchus, by using complex measurements, which I don't have time to go into here, complex measurements and huge deductions of geometric reasoning, was able to find the size of the sun and moon. And these figures, when Aristarchus found them, were shocking. The sun is many, many, many times the size of the Earth. And so what this made Aristarchus think, he said, why on earth would a way larger object go around us? We're small in comparison to the sun. Why then would it not be the other way around? The tail doesn't wag the dog wags the tail. Why doesn't the sun move the Earth? And so Aristarchus had this hypothesis, but was generally considered to be a crazy man because he thought that the Earth moved. And of course, the main reason that people couldn't accept that the Earth moved is they would just say, well, why don't I feel like I'm moving? And Aristarchus did not have a response to this. Now, after this, mankind suffered or at least mankind in the West suffered a huge period of basically no scientific progress. So we'll have to fast forward many hundreds of years to our next hero, Copernicus. Now, Copernicus was on board with Aristarchus. He didn't think that the epicycles were a good explanation of this planetary motion that we see in the sky. And so what Copernicus did is he made a new model of the heavens. He placed the sun at the center, and he made various angle measurements between the sun and the various planets. And by working all of this out geometrically, Copernicus was able to identify the sizes of each of the orbits. And based on those sizes, he was able to calculate the order of the planets, and he was able to calculate their speeds as they went around the sun, assuming they went around the sun. The results were shocking. The order that Copernicus came up with was that Mercury is the first planet from the sun, Venus the second, Earth the third, Mars the fourth, Jupiter the fifth, and Saturn the sixth. They didn't know about the other planets back then. And further, not only did he come up with this order, which he would not have been able to, prove, this is just assuming the sun is at the center. But once he considered the planets in this order, he was able to calculate their speeds, assuming that all of these all this modeling and setup was actually correct. And what he found was truly remarkable. He found that the closer planets were faster and the further planets were slower. The fastest moving planet is Mercury. The second fastest moving planet is Venus. The third fastest moving planet is the Earth, and so on. Copernicus was then able to conclude that the sun, as though sitting on a kingly throne, governs the family of planets which wheel around it. And so at this point, there is very strong evidence that the sun is at the center. But there's still this incredible counter-argument to Copernicus's theory, which is, of course, well, why the hell does it feel like the Earth isn't moving, you lunatic, right? But the thing is that counter-argument is actually making a bunch of incorrect assumptions about the nature of motion. And to overturn these faulty counter-arguments, we needed the knowledge of Galileo, our next hero. Galileo did a bunch of work on understanding motion. And two of the things that we'll go over in this history is he understood the nature of falling. He understood that when an object falls, it accelerates at a constant rate. Okay? And all objects accelerate at that same rate when they fall, is what Galileo found. Through further understandings of motion, Galileo was able to form an extremely important law of motion. And that is that motion does not require force. Motion, once an object is in motion, it will simply continue its motion. Force is not required for motion. Force, rather, causes a change in motion. It causes acceleration. Now, people would argue against this by saying, well, wait a second. When you slide something across a table, it comes to a stop. Why? Well, because you're not continuing to push it. But Galileo said, no. You have to ask, why does the object come to a stop as you slide it across the table? Well, it comes to a stop because it's rubbing against the table. The force of friction causes it to decelerate. In an absence of such a force, it would not decelerate. It would continue with its motion. And we can see this by lubricating the table, maybe greasing it up and then sliding the object again. And when we do this, we find that the object will lose its speed much more slowly when we make the table slippery. And so Galileo, by coming up with this law of motion, allowed us to see that it makes perfect sense that the Earth could go around the sun and we wouldn't feel it. So long as we maintain a constant speed around the sun, which according to Copernicus we do, we would not feel the actual, no force is required to keep us moving around the sun. So we wouldn't feel like we were getting pushed around all the time. We just have the motion that we have. And so Galileo was able to give a counter-argument against this argument against Copernicus's theory, that the sun is at the center and that it causes the motion of the planets. Now, unfortunately, at this point in history, the epicycle theory was actually still more accurate when predicting the motions of the heavens. And most of this was because that every time some sort of inconsistency with actual observations was found, theorists or mathematicians would simply stack another epicycle on top of the epicycle. So you have circles on circles on circles, each one made to sort of make minor corrections. But this is not the real way science works. In science, we have to identify cause and effect. We don't just come up with some arbitrary model, which we like because it has these perfect spheres in it and reproduces the observations. No, that doesn't allow us to progress. And science and astronomy indeed stagnated for 1,000 years as this theory was simply accepted. But fortunately, our next hero, like Copernicus, did not accept that theory. His name was Kepler, and he came up with laws governing the motion of those planets. And he came up with many of them, but the one that I will show you is this, his third law. He was able to see that there's a pattern, there's a correlation between the distance of each planet from the sun and the amount of time it takes to go around the sun. Here, T is the planet's period or its year, the amount of time it takes to go around the sun, and r is its distance from the sun. Okay? And so that then leads us to our next hero, the hero among heroes, Isaac Newton. Newton thought about the motion of the planets in terms of motions that we see here on Earth. He didn't think that all of this was governed by some kind of heavenly force that we just will never understand. Newton saw this as the motion of bodies, of matter in motion. And so when he looked at the motion of the planets, he said to himself this. He said, Galileo tells us that once an object is in motion, it will stay in motion. It will continue just going the direction it is. Well, if that's the case, then why is it that the Earth is going in circles? Why doesn't it just go in a straight line? Well, one way to think of this, says Newton, perhaps the sun is pulling the Earth towards the center. And what this does is it causes the Earth to always turn. And the Earth is moving forward, but always turning, causing it to go in a circle. And so what Newton said is, he said, well, there must be some kind of force emanating from the sun. What's the nature of this force, Newton asks. And what he does is he takes he works out the mathematical, he works out the amount of acceleration required to actually get an object to move in a circle, the amount of turning that the Earth would have to do in order to actually go in a circle. And then he combines that mathematics with Kepler's third law. He finds that the sun must be exerting a force on the Earth, which is inversely proportional to the square of its distance. The further out you get from the sun, the weaker the force gets as the square of the distance. And so Newton says, well, perhaps this is the force that keeps the Earth locked in the Earth and the other planets locked in circular motion around the sun. Then, as history tells us, as the story goes, on one calm day on his sheep farm, Newton is sitting under a tree reading. And as he's reading, an apple falls from the tree above him and hits him on the head. And he looks up, and this is my story, by the way. I don't know if this literally happened, but maybe it happened this way. Newton looks up, and he sees the moon directly overhead. And he says to himself, oh, well, that's funny. The moon is going in a circle around the Earth. So right now, because the moon is directly overhead, the moon is accelerating directly towards me. And then he realizes, the moon is accelerating towards me. The apple, Galileo teaches me, is also accelerating towards me. What if they have the same cause? And so what Newton does is he applies his inverse square law to both the moon and the apple, and he finds that the inverse square law, the force caused by a central body on the bodies around it, is able to explain the motion of both the moon and the apple. This further leads him to suspect that every piece of mass in the universe is attracted to every other piece of mass. This is his law of gravitation. Newton then proves this law of gravitation by explaining the tides. He's able to predict when the water will rise and fall by calculating the gravitational pull, using his inverse square law, calculating the gravitational pull of the moon, the Earth, and the sun on each individual piece of water on the Earth. And by doing this, he's able to predict the tides, thus proving his theory of gravitation, that all mass is attracted to all other mass. Newton did not stop there. He went on to write an entire book explaining not only his law of gravitation, but the laws of motion and force in general, which on their own, this book on its own, made mankind a master of matter and motion. We now understand how forces add up in order to cause objects to accelerate, changing their speed and thus dictating their motion. So by standing on the shoulders of giants, Newton was able to unify the heavens and the earth. He was able to show us that the laws down here on Earth of objects falling and of forces accelerating things are the same laws that cause the motion of the heavens. Now, that's going to end our video for today. But the journey does not stop here. It has only just begun. So I hope you'll join me for part 2 of the history of physics.